Hello everyone and welcome back to this next lecture. So in the previous few lectures, we had started with the rotating reference frame. So now that we had talked about the rotating reference frame and we had also implemented in a simulation, we now have to go ahead with using this rotating reference frame in our control. So the first step is we need to generate a model for this rotating for our system in the rotating reference frame. Right? When I mean a model, I mean exactly the similar model that we had in the previous section with which we had created controllers. Now the question you might ask is, why do we need another model? The reason is that this particular differential equation that we had used in the previous section is something that can be written in the stationary reference frame. Right? Now it's important to understand that this differential equation is when all these variables are measured without any concept of motion in the reference frame. So therefore, quite obviously, they are written in the stationary reference frame. Now, you cannot directly replicate all these variables with variables in the rotating reference frame. It's quite obvious because remember, we are performing a transformation. It's not just a variable substitution. So now, how do we do that? We do that first and foremost by knowing that this differential equation can be written for both axes in the stationary reference frame. So it can be written for the x-axis as well as the y-axis in the stationary reference frame. Right? Because remember, as long as our reference frame is stationary, these laws which are physical laws, this is a Kirchhoff's voltage law. This Kirchhoff's voltage law will always hold true, right? So whichever reference frame, but rather whichever axis you look at in the stationary reference frame, this law and even other network laws like Kirchhoff's current law will hold true. So therefore we can write them directly for every reference frame in this manner. So all I'm doing is I'm appending an x and a y subscript to each and every variable. So we have these two equations. Alright, we have these two equations. They are almost identical except for the fact that the subscript is different for each and every variable. So now that we have these two variables, we can write them as a single matrix equation. Right? So we are basically collecting all these variables as vectors and matrices, and we are writing it in this form. Right? Just nothing special, just converting a group of equations into a single matrix equation. This is the advantage of writing equations as matrix equations, because you can express them all as one single equation. So now we already have derived expressions for representing the projection of the voltage phasor on the rotating reference frame with respect to the projections of the voltage phasor on the stationary reference frame, and vice versa. So we have expressed Vx star and Vy star in terms of Vx, Vy, and we have expressed Vx and Vy in terms of Vx star and Vy star. So this has been done already in the past few lectures. So we can use these relations in this particular equation, right? Because remember, we can these expressions hold for each and every variable, not just the voltages. It holds for each and every variable. Any AC quantity can be represented as a phasor, and that phasor will have projections on the stationary reference frame and the rotating reference frame. So we can write this for each and every variable, for the voltage, for the current, for the grid voltage as well, right? So let's keep going. So what actually happens is, if we substitute the variables, so like for example, if we substitute these variables with the corresponding variables in the rotating reference frame, we get something like this, right? So you see, this is just substituting of variables. I am trying to express my stationary reference frame equation as now a rotating reference frame equation. So I am performing a variable transformation. Now you see that this ends up with these matrix multiplications, or rather pre-multiplications, left multiplications with the matrix T inverse, right? And you see this term happening everywhere. Now if I want, I can multiply this entire equation by the transformation matrix T, right? You can multiply any equation, both sides of the equation, left hand side and right hand side, by any variable or constant, and it does not change the equation. This is fundamental mathematics. So which means I can multiply both sides and the 0 on the right hand side remains the same. But you see now that this TT inverse in most of these results in a simplification. Quite obviously, T into T inverse is 1 or unity. It's a unity matrix, or I would say an identity matrix, right? Because it has 1 on the diagonal. Also, when you multiply it in this manner, that is T multiplied by a diagonal matrix multiplied by T inverse, you end up with the diagonal matrix itself. So T inverse can actually be brought out and it again cancels out. So the T cancels out on the first term, the third term and the fourth term, right? So all these terms, the first, third and fourth, are free of the T variable. The only term that remains is the second term. So let's have a look at this. Now the differential of T inverse multiplied by the projection of the current on the rotating reference frame can be spread out in this manner. So it is a sum of the product of the differential, right? The differential of the transformation matrix and the currents in the rotating reference frame plus the inverse of the matrix and the multiplied by the differential of the currents in the rotating reference frame with respect to time, right? This is very basic calculus, that is, this is the law of differentials, right? When you differentiate a product, it is just like d by dt of A into B is A d by dt, or rather d by dt of B, and plus B d by dt of A. This is very simple law of derivatives. Now what that means is we can now calculate this entire thing. So for example, we can differentiate this T inverse, right? This T inverse that is here, this matrix, we can calculate the differential and we can now open up the rest of the equation. So we can calculate the entire expression with respect to this, that is TL multiplied by this. And if we do this, if we calculate it, and I would suggest take a piece of paper and try it out yourself, you will get this equation, right? You will get this equation. So what this means is that this third term, or rather second term, actually breaks up into two different terms, right? Now with this we can write the following expression. We can say that the differential equation in the rotating reference frame is of this order, right? Now it seems identical, but there's one difference. The difference is that there is now a coupling between the x-axis and the y-axis. You see that coupling is there. There are now off-diagonal terms in this particular matrix. And if we compare it with the equation in the stationary reference frame, we see that these two equations are completely decoupled. All the diagonal matrices, all the matrices, the square matrices, are diagonal matrices. They do not have an off-diagonal element, right? So these two, this equation, even though it's a matrix equation, there are two separate equations that have nothing to do with each other. Whereas here, that is no longer the case. Now these equations, that is the equation for the x-axis in the rotating reference frame and the y-axis in the rotating reference frame, they now have a relationship, right? So the conclusion is the differential equation. The good news is the differential equation is not very different. So we haven't landed up with something that is totally out of this world. It is still something that is familiar. The only change that we need to account for is this cross coupling. And this does play an effect, because what it means is whatever we do to one variable will affect the other variable as well. They are now coupled together. But we can eliminate this coupling when we implement control. That's the good news. So what we are going to use going forward is this equation. This is our mathematical model for the grid connected converter in the rotating reference frame, where we have two axes, the x-axis and the y-axis, and these are the equations in the two axes. So again, most of all this is just simple calculation, matrix multiplications, computations. I would strongly say take a piece of paper and just write out all these equations once yourself and clarify it for yourself that this is indeed the case, right? So in the next lecture, I'm going to talk about how we will use this model in implementing control. And very soon after that, we will actually implement control. So if you have any doubt, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture. Thank you so much and see you soon. Goodbye for now.